You're able to see the screen, right? Yeah.
Yes, sir.
Okay. So anyway, so last class, we already seen this size frequency distribution. Okay, so how do we do this lunar? That is a geological time scales. How do we get for the moon? Okay, so the most important thing what we have seen is what we call as the production functions or whatever people call them. Okay, that is a lunar production functions. They say. So two things that is what is widely used. This one. One is this. The Hartmann production function they say, okay, which is just a straight lines. So the size frequency distribution you take and then you fit a straight lines, like you see one straight line here, one straight line here, like that. So this is how we can construct a size frequency distribution. Of course, this is on cumulative plot as well as in the R plot. That is a derivative of this itself. Okay. So anyway, this size frequency distribution is also known as isochrone also. Both of them are same. So we will try to do by this one also. Now other thing is this Newman, the production function they say, where instead of fitting a straight lines you say, so you fit a polynomial, instead of doing that one, because a polynomial means you can do the derivatives and it is very easy to calculate all those things, and it also will be smooth, the kind of thing itself. So these are the coefficients, A0, A1. So sometimes they use 11th degree, 10th degree, so that depends on the data. Like you see, you fit to the data and then you decide, say, what order polynomial, you have to use and you have to decide. Okay. So this also I showed you in the last class. So this is how the Newcomb's, so this Newcomb production function say, how it fits to the data because it's a polynomial. So you will see this type of wavy structure. So what they claim is, the data is also like a wavy structure say. So instead of fitting a straight line, we can fit a wavy kind of a thing. That is essentially this polynomial. Okay, so this also we saw in the last class. And then finally say, so for moon, the main advantage is that you see human missions went. So Apollo 11, Apollo 12 say rocks have been brought, and then the carbon dating is in the lab, those things have been done. So now what people have done is they have compared this carbon dating, say this whatever this with the size frequency distributions, and then they have done this calibrations. Okay, so the what is that? So you remember last class, how do you find out the age? No. So what is that we told in the last class? How do we find out the age of the crater? Like once you know the size frequency distribution, so like if I want to find out a Copernicus crater or some crater you have found on moon, say, okay, and you want to find out the absolute age, basically, like what time when this crater has been formed, say. So our first step is you do the size frequency distribution. You find out all the nearby craters or whatever in that region, and then you find out the size frequency distribution, say. Now from the size frequency distribution, say what is that you have to estimate to find out the absolute age. So last class I told you, say what is the most important thing?
N of 1.
N of 1, that is the n value. So that's the crater density at 1 kilometer or whatever. So this you have to find out. So this and age say. So this age has been found out from the Apollo missions. Okay, the carbon dating. So this is a graph. It looks like it is something like a curve. It looks like that. So if you want to do the age of Copernicus crater, say you find out size frequency distribution. You find out n of 1, say, and then you plot in this graph, automatically you will get the age, that is the absolute age of that crater itself. So this is the philosophy. Okay, so now of course people have done so many things also, like if you are having craters which are less than 1 kilometer diameter, so use this curve, and if it is more than 20 kilometers, so you can use this type of a curve, and the people have tried to fit this type of equation also. So this also I showed you in the last class. Okay, n of 1 say. So from the data they have fitted like exponential things are there, then linear things are there. So when time is very small, say, okay, when t is very small, you will see a linear kind of thing. But when as a t this one say, then you will see like this. Okay, but of course for moon, please remember. So origin means that is a current age. That is how they plot these values. Okay, and 4.5 billion years, so that is in the past. So that is how these functions have been plotted here. Okay. So this type of, so the main thing is, your n of 1. So if you know n of 1, say, you can easily, from this graph, you can plot it and then you can get the age. So this is how, people have found out, like Copernicus crater, Tycho crater, say. So they did found out n of 1 for this. If you plot in this graph, it looks somewhere here. So the age of Tycho crater is this much. That is how we try to estimate the ages of the craters, absolute ages. So that's what. So this is how the A naught. That's what we said. Okay, n of 1 and others we told in the last class itself. So anyway, so this is how people have estimated for the moon itself. That is a geological age of things itself. Okay. Now, how do we do these impact craters on other planets? Basically, like if I want to find out on Mars or Venus, and of course Earth also, we don't know. Basically, in Earth also we may have so many craters, but all of them got destroyed, because of weathering and plate tectonics and others also. So if you want to find out, say, the size, frequency, distribution, or the chronology, the lunar chronology, say, you want to translate it to other planets, how do we do this one? So here also people have tried actually. Okay, so that I will show you, how do we estimate this type of chronology for other planets itself. So the most important things is, if I want to compare Moon and then Mars and then other planets, say, the most important thing is, so your, the impact rate basically. Okay, this is a very important thing. See, like for example, if you see, the Mars, say, see the impact rate for you. If you see this figure, say, impact rate for which terrestrial planet is very high. Now, if you see the second column, can you point out which has more impact rate? So which terrestrial planet has more impact rate, average impact rate? See the second column. So that is a third column, average impact rate. If you see which has highest impact rate, if you see this one,
Mars.
Why Mars has more impact rate compared to Earth, Moon, Venus, and Mercury?
It is nearer to the asteroids.
So that's what you say. So you are near asteroid belt, so that also matters basically. Okay. So now So what people says now, the lunar chronology of moon, say. If you want to translate it to other planets, say the most important thing what one should have an idea is what is the average impact rate has to be found out. Okay. So this is the most important thing. Then probability also, because the chance of that asteroid crossing the orbit, say, of that planet, so that also becomes very important. So if I know impact rate, then average collision, and then average impact velocity. See, this is a very, very important thing. So this depends on the gravity of the planet. Okay. So the impact velocity is very high, say. You have seen, right, those numerical simulations. Diameter is same, but impact velocity is so high, say, then crater dimensions will be different actually. So moon crater dimensions, so same projectile, same diameter, everything, but the velocity is different. So the crater diameter will be different. So this also is a very, very important. So if I know these things, basically, that is average impact rate, then average collision, that is a probability. So that is, impact rate is one thing, but the probability depends on, the crossing the orbit, basically. So if that asteroid, so many asteroids are crossing the orbits of the planets, say, then, the probability also increases, basically. Okay. Like if you see the probability, say, like for which terrestrial planet is very high? Now, the impact rate for Mars is high, but if you see the collision probability, say, so probability is high for which planet? Now, can you see this third column?
Venus.
Venus basically. Okay, so because there may be a chance. Okay, then the impact velocity, say. Then we also have one thing what they call as this bolide ratio also. So this bolide is something like it is something like when you're having an atmosphere, say. So when there is atmosphere, like for example on moon, say, since there is no atmosphere, say, so the impact will, the projectile diameter will be same. But on Earth or other planets, if there is atmosphere, because of atmospheric the pressure or friction or whatever, so these impactors, say, may break into pieces in the the atmosphere itself. Okay, so this also matters a lot. So now what if I know all these four things basically, then we can translate. If I know for moon, say, I have to just correct this graph, whatever graph was plotted for moon, say. So this, if I want to translate it to Mars or this one, so what you have to do is these parameters, if you take care, if you correct for all those four parameters, then you can easily translate it to other planets also. I will just show you, how do we do that itself. Okay, so that's what we said. Okay, so this also we discussed in the last class itself. So the frequency of impact velocity, so these are all very important basically, okay, to translate from one planet to another planet itself. So this was the histograms people have observed from the planet, the satellites and other things also. So these numbers are also known nowadays. Okay, and now as already I told you, the topography data sets are available, because of several missions. So all the craters have been modeled from the data. Of course, some more craters they would have missed also, but these are some of the craters. Like in Mercury, we have this crater database. Then Venus also we have crater database itself. So here what, just if you plot say cumulative crater frequency, that is, you count the number of craters basically, like I want to count the number of craters which have diameter more than 1 kilometer. Okay. So you count all these numbers, and if I want to count all of more than 0 kilometer, means everything will come into picture. More than 1 kilometer you count, more than 2 kilometer you count, more than 3 kilometer you count. Like that, you count up to the maximum crater diameter and then divide by the area of the planet itself, the surface area. So you will get this graph. Basically, that's what we will get: cumulative crater frequency versus the diameter. Say if you plot the data as it is, which you have got from the QGIS or something. So this is how the graph looks like basically. Okay, so you can see what is the maximum diameter on Mercury, the highest diameter. So what's the largest crater diameter? Can you see this x-axis? Or if you compare Mercury and Venus, which has the largest crater? See the crater maximum crater diameter. Where do you see the largest crater compared to Mercury and Venus? No.
Mercury.
Mercury. So you can see this is 1,000 kilometers, so 10 cube basically. So this may be somewhere around 1,500 kilometer or something. Now when it comes to Venus, this is 100 kilometer, 200 kilometer, 250 kilometer. What will be the reason for this? So this also, the reason could be, if you see this table, so you can easily find out basically. Okay. So now on Mercury, so now if you see this, that's 1, 2, 3, fifth column, that's impact velocity. Now what happens? Which will have the largest craters? If you see this graph, which will have the largest craters? Why Mercury's diameter, that crater diameter, is more than Venus? Can you tell the reason?
Impact velocity for Mercury is higher.
Very high. So the impact velocity is high. So obviously it penetrates a lot of the distance itself. So that's why you will see large craters in Mercury itself. And anyway, these is how the size frequency distribution from the data. So if you plot as it is, you will get these type of numbers itself. And now if you see for Earth, of course Earth graph, we can't follow, right? Because many of the older craters have been erased. Only thing whatever we are seeing is only 250 million years are very recent craters only. Of course, recent means in geological ages. We don't have like 1 billion year, those type of craters itself. So this is how it comes. Now, what is the largest diameter? Can you see the diameter on Earth? Can you see in this graph? So this is 100, then 200, then you are having a 250 kilometers actual. Okay. So this is the largest crater which has been observed on the Earth itself. And then if you see Moon, anyway, we have already seen Moon, and then Mars also. So these are all the data sets. Okay. So these craters have been found out, and then all those things have been done. And if you try to plot, now then Moon, what is the largest diameter? Can you see that? That largest region? No. So this is almost 2,500 or something. It comes on Moon. Where what is it? Nah, you remember the name, right? Which is the largest crater on Moon?
South Pole at
South Pole Basin. Okay, very good. South Pole, that Atkin. And now if you see on Mars, so now on Mars, what is the largest one? So you can say 1,000. Then maybe it has more number of things itself on Mars. See why Mars diameters are very long? What could be the reason? So if you see this graphs, what could be the reason? See the impact velocities. Of course, it has some eccentricity, they say, but why it is on Mars? You are having large diameters or large things. You can compare, because impact rates for Mars is very high, because it is very close to the asteroid belt. Okay, so you giving these things also, one can see why it is high, why it is not high, or if you can easily compare also. So if you see it starts with the 10 to the power of 1, then 10 to the power of 0. See, on Mercury, small craters have not been identified. Okay, because maybe we don't have the high resolution images. Venus, you can compare these numbers also, the y-axis also. So Venus means 10 to the power of -5. You can see Mercury is 10 to the power of -4. More number of craters are there. And the Earth is 10 to the power of -6, because many of the older craters have been erased also. Then moon and this one, if you compare, say 10 to the power -4, you can see the Mars itself. So this is how the data looks like actually. If you just try to compare the size frequency distributions at all the data set, it looks something like this. Of course, this they have plotted for the entire planet, okay? But if you want to find out age, say, so then geological classifications, you have to repeat this for small regions, okay, of the entire planet. Then you can find out the relative ages and then absolute ages by correlating with n of 1 with the moon and other things also, okay. So now how do we transfer? So this is a chronological model transfer from the moon to other planetary bodies. See why moon is very well established. The reason is, human missions went, we have samples from there, and then we have tested in the laboratory, and then on moon, so there is no atmosphere, okay, no weathering or nothing has happened. So moon preserves nicely, all the 4 billion years ago, the history, everything is nicely preserved in moon itself. But if you see Mars, then Venus, they have atmospheres also, like wind, air dance. I showed it a long time back itself. So many complication things are there. So it is not that easy to find out the geological ages of craters or whatever regions in those planets. So what one does, what people have attempted is also like very well for the moon, say. So how do we transfer this information to other planets? Even for Earth also, we don't know the chronological things because it got eroded. So how do we use this information also? So there are a lot of people have worked, some Hartmann, many papers are that you can easily find out in Google, So most of the textbooks are not there in this area. So you can several research articles like in JGR and others, so many things have been done. But now what they do is, so this is what they say. So the standard cratering methodology say. So what they say is a monotonically smoothly decaying cratering rate is assumed basically. So this is assumed for all the planets. And then, for all the planets, say, if you see moon, Mars or Venus or whatever, the main assumption say in this whole analysis is around 3.9 billion years. That is in the olden time, the cratering rate say, for that means when the solar system was formed some 4 billion years or 5 billion years ago. So at that time, as already I told you, right, solar system gets formed due to impacts only, okay. So at that time, there was like, a uniform impact, and everywhere the impact cratering rate was same actually in the olden days. Now things have decreased. So this is an assumption. So 3.9 billion years ago, say. So the impact rate on Earth, impact rate on Mars, impact rate on Moon, all of them were set. So this is how they assume. And then they have derived this, the lunar the transfer. That's a chronological model from Moon to other, this planetary bodies also. So these are how, they started. So these are the steps actually. Now I know for moon, now how do I draw this graph or how do I translate this graph to other planets? So they have some 4 steps they say. That is the first one is lunar impact velocity distribution. Now from the moon say, I know this graph, okay. So what we are trying to say is this graph is known to me, okay. So this is a graph basically. So this graph I know age versus cumulative crater frequency. So this graph I know very well for moon. Now I want to translate this graph to other planets. And other planets, Venus or Mercury, so we don't have much idea or whatever, this one. So I want to translate this here itself. So how do I translate? So for this, we have to have the 4 steps. So that graph is from the craters basically. So now you have to find out what was the impact velocity distribution on moon, because your crater highly depends on the velocity and the size of the diameter and so many things are there. So this has to be found out, the impact velocity. Once you know this one, so then the projectiles say. Now that whatever graphs I showed you, these are for the craters. Okay, the crater size versus crater frequency. Now what we have to find out is from this graph say, the simple thing is, can I find out the frequency distribution of the projectile, that is impactor itself, or the asteroid say. So because anyway, asteroid only has created this crater, and I already showed you the scaling laws also, previous classes itself, like, if I know the impactor size, its velocity, and then its density, and then its angle or something, you can even easily find out is how much will be the crater diameter, rim diameter, and all the scaling laws are there. So what now from the data set you can get this information, that is a crater frequency versus crater diameter you can get. Now this graph has to be converted into the projectile, this one, that is the size frequency distribution of the projectile. So this is the next step basically. Okay, this also have to be done. Now, after this is said, now which planet you are talking about? Suppose if you are talking about Mercury, Venus, or whatever, you should know the impact probability and then impact velocity distribution for the target planet. So this information you should be known to you. Okay. Now, once you know all this information here, now you have to find out the calculation of crater size frequency distribution on the target planets using the lunar direct projectile size frequency distribution. So this is how we do. So 4 steps for moon. Already we know the chronological, that graph is already there. Now I want to convert this to Mercury or Mars or something. So the steps is first lunar impact velocity, then the projectile size frequency, then impact probability of the target planet, and then once again we go to the crater size frequency distribution itself. So this is what you see we are trying to, the people try to do to find out for other planets itself. Okay, without sending a probe or something, just translating this information also. So this is a step one, they say. So now, as already I told you, the lunar impact velocities you can easily derive based on, you see, the probability estimates for near Earth asteroids. Nowadays we have the telescopes. You know how many asteroids are there. You know, with Earth crossing orbits. This you can easily find out basically, and then you can find out this probability itself. Okay, that's the probability of impact with a given velocity. That is FU of U. You can easily find out from that data itself. Now the second step, say, so this is easily you can do. So the lunar impact velocity distribution, say, you go, you see in a telescope, already the data is there, asteroids, which orbit they are colliding, you see, you can easily find out the, this impact, whether it's a probability density function for the velocity. Now from the next steps, you have to find out the projectile, that is the size frequency distribution of the impactor or the projectiles. Now this, anyway, this comes from your total probability theorem. I don't know how many of you have done the probability course itself. You know, like if you want to have that sample space, the total probability theorem is there. Like if I want to find out probability, of any event, say like probability of A, greater than Y star or whatever. So you have to use the total probability theorem. So here your impact or the crater diameter. So the crater diameter, whatever you are seeing in the graph, it depends on the impactor velocity, impactor size, and then the impact angle. So these are the three main parameters itself. So if I want to find out the probability of the crater, like, if there is impact, what is the probability that my crater diameter will be more than 10 kilometers, say, okay. So, you should know that depends on the probability, that is the velocity of the impactor will be, that is also one aspect, then angle of impact is also another aspect, then the diameter of the projectile. So these are the three main variables. That's what is said, dp, then u is the velocity, phi is the angle. So these are the three. So your crater diameter, say, so d, that depends on dp, u, and phi actually. So now if I want to find the probability of this one, say, anyway, probability frequency, both of them are same only. So it depends on these three quantities. You can get it from the total probability theorem. That comes from this integral here. So this is u min to u max actually. As already I told you, right? What is the impact velocity distribution, say, for moon? This is a graph. You can see 1, 2, 3, fourth one. That is for the moon. It is a probability density. So the impact velocity can anyway, this is a 5, 10, 10 is here. So almost 3 kilometer or 4 kilometer to maximum is 35 to or 36 kilometers. So this density is on the probability density also. So this, and then you have to find out the probability density function for the angle. This also one has to find out. And then the projectile diameters. Okay. So this you can easily get from the scaling laws. Okay. So using this expression, say, so this is our, this one. Now we have to find out dn by dtp. So this is what we are interested in. There's the size frequency distribution of the projectiles. So you have to solve this, the integral equation to solve for dn by dp. Now I know dn by dd from the data, okay, and fu of u I know from the data, and fi of phi also I can estimate from some this type of equations, and I know u max, u min, phi min 90 degrees also we know. So I want to calculate dn by ddp. Okay, so this is what we are interested basically. Okay, so you have to solve this integral equation. So if you once this is solved, so you will get dn by dp for moon itself. Okay, so this you have to do. Now, generally in practice, what people do is this they omit actually, because angle is not so important, to simplify the analysis because we don't know these things. So once, they take as a most probable angle as a 45 degrees, and then to make it very simple. So then if this is the case, say, and if you take mean value and average impact velocity and then 45 degrees if you take, so like you say, this is a 45 and then only one value. So 45 degrees is this one. So this integral vanishes, 5 into 90. So this becomes a direct delta function. So delta 5 minus 45 or something it comes. So and then u max also, if you take to be average this one, say, so then automatically one can show that, dn by dp is dn by dt. This is a special case. Otherwise, you have to do those calculations itself. Okay. And of course, apart from this, say, okay, like previously we have, seen those numerical things also. Apart from the projectile diameter, velocity, and angle, density also plays a major role. Whether it's iron meteorite or what is the density and other things also. So people have tried like two different porous thing and then non-porous, because comets will have less density, but asteroids will have more density. So this also has been you followed, right? One can use it. So these two steps are done. So one, the lunar impact velocity distribution, then the projectile size frequency distribution. So these two are done. Now the next thing is impact probability of the target planet. So let us say I have the the target planet. I want to find out for Mars, say. So impact probability, impact velocity. So it depends on the orbits of small bodies. I told you, right? Mars will have maybe more impact rate. You have to calculate all those things itself. And average impact velocity is already known. I showed you those graphs. That histograms are already people have estimated here also. Then average impact rate. So this you have to understand the orbital dynamics actually. Okay, so here your celestial mechanics, those people will help you, like what is the orbits of the asteroids and comets, so what is the intersection between these two, and the probabilities they estimate. Okay, so there are many papers and other things are there. So from those things, so you can estimate impact rate, all those things can be done. So this also I showed you, the previous graph also, the same thing. Okay, so like Mercury's impact rate is 0.684 10 to the power of minus 15 per kilometer square per year. Then the collision probability is 1.651. Of course, it is in billion years or whatever. Then the impact velocity, this is an average value. Okay, so these numbers are there. So these numbers have been come from the observations of asteroids and comets itself. Okay, so once this is a probability estimates also, like you see the projectiles, what is the probability of impact per year, like what's the probability of 10 kilometer size projectile touching the earth surface, or what's the probability that 0.1 kilometer projectiles are touching the earth surface. So you can see, so if you see here, so what's the probability of impact for 10 kilometer projectiles to impact earth, what's the probability? Can you see here in a given year, say, so like this year, what is the probability that our earth will be impacted by a projectile of size 10 kilometer, a huge asteroid will hit earth basically. What is the probability? Can you see this graph? Now what is the probability? So what is the probability of 10 kilometer impact hitting earth this year? Now, how much is the value? Can you read this? What is the value?
So 10 raised to minus 8.
10 to the power of minus 8. What does it tells you? What is the reciprocal of probability? So probability is also frequency only. Both of them are same only. What is the reciprocal of frequency? So reciprocal of frequency, what do you call that quantity? Reciprocal of frequency.
Time period.
Yeah, that is a time period. Reciprocal of frequency is time period. Reciprocal of probabilities. I think Utkarsh may be knowing, he would have studied in design courses and others. What's the reciprocal of probability? See, in our wind code also we use, right, that word. Reciprocal of frequency is a time period. Reciprocal of probabilities. Utkarsh, do you remember?
Sir,
So you don't remember. So what reciprocal of probabilities? Return period actually followed. So return period we say frequency is a time period, probability is return period itself. So now for 10 kilometers, so what is the return period?
10 raised to 8.
So what does it tells you? So 10 kilometer meteorite asteroid hitting Earth, say return period is 10 to the power of 8 years actually. Okay. Now if you take 0.01, say, like these are 100 meters basically, right? 0.01 or whatever. So this much kilometer, so you can see 0.1 or whatever, then you can see 0.001, say, extremely high actually followed. So these how the probability impacts this. So this also you have to estimate from the data and other things also. So now once I know the these all these numbers, say impact rate, collision probability, everything if you know, say, then you can estimate basically. That is a step 4. Okay. So now a crater size frequency distributions is you calculated using the lunar derived projectile size frequency distribution. Okay. So now, you have to correct for all those things itself. Now then you know the size frequency distribution of the projectile. So once you know the size frequency distribution of the projectile cell, now it is very easy to calculate size frequency distribution of the diameter. So you can use the same equation itself. Okay. But FU of U will be different. See, previously from the moon, what happened was from the moon, say dN by dd is known from the data. Knowing dN by dd, knowing the probability density function of impact velocity on moon, then probability density function of impact angle on moon, we found out dN by d dp basically. Now what we are trying to do is, once a dN by d dp is known, now we have to find out dN by dd for Earth, actually other planet. So now to find out dN by dd on Earth, say, what we are using is this dN by ddp, which you have calculated for moon, you substitute here, but FU of U, you have to use the probability density function for Earth, then Fi of Y, so you have to use the probability density function for angle on Earth itself. And if you want to do for Mars, say, so what happens is dN by ddp is same for any planet, okay, because that is depending on only the size frequency distribution of the projectiles, okay, so that is done. But now FU of U, Fi of Y, and all those things, that is different for different planets. So substitute in these equations, I will get dN by dd for my planet. So this is a philosophy. The same equation. So first you are solving reverse, then you are doing the same equation, but the probability density functions are different. So this is how people use it in practice. And that is what we do. That's a step 4 basically. So now using that one. So here also you have to use some scaling laws, because you know the size frequency distribution of the projectile, say. Now you have to find out size frequency distribution of the crater. So crater thing, you know that the scaling laws, I already long back itself we have seen, like to see if I know the projectile velocity, projectile diameter, projectile listing, and knowing the gravity of that particular planet, you can easily find out the crater dimension. So that you can use, and then you can find out the crater size frequency distribution, you know, for your corresponding planet itself. So this is how we do. Okay. And of course, so the main advantage of people regularly use this one is, so Earth and Moon, say, they are subjected to same projectile flux. That's impact rates are more or less the same. So these are, so generally, whenever you do this type of development methodology, the first thing is you calculate for Earth, and then you validate whether this works or not. Okay. And as already I told you, for Moon, we have reasonable reliable crater counts. Moon is a very, very reliable thing. Okay, because of no atmosphere, everything is nicely preserved on Moon. So then, of course, human missions also went. We have the rocks also, and they've nicely calibrated basically. Okay, so and of course, most of course, the only negative thing this graph say. If you see this graph, it is based on what data? So this graph, if you see, say. So this graph is based on which data? Can you see here? What are these data sets? If you see this graph, that is the second one, B. So this figure is based on what data? This calibration has been done basically from
Apollo missions.
From
Apollo missions.
Only Apollo missions. Apollo missions where they have landed, Apollo missions, most of the Apollo missions, they were only on the near side of the moon, but far side of the moon, we have no idea. You understand? So anyway, this is the only, the limitation or whatever with this graphs itself. Okay, so this is the only thing. But anyway, that is a good, the starting point. That's what they say. So most available crater counts are for lunar mare. This has been typically, that's what the thing. But on Earth, say, the only thing is, Earth, so craters are there, but many craters have been destroyed actually because of plate tectonics. Every 250 million years, say, new things gets formed, and this one 2/3 of Earth's surface gets changed actually because of plate tectonics. But whatever craters are there on Earth, say, like Lunar crater, Ramgad crater, Dhalo crater, people have done isotope dating because it is on Earth only. People have done a lot of papers, and everything is there. And meteoroid entries, that also we have very good data. The frequency, the impact probabilities are very there. And then one more thing was, as already I told, how moon formed in our solar system, the Earth Moon bombardment. They say that, both of them, the theory, now it is very well accepted that around 4.5 billion years, both Earth Moon formed at the same point of a time. I told you right last time that many models have been done, but now recent it is very this thing that there were two planets which collided with each other, and then moon formed above this one. So the moon has been formed, Earth's Roche limit actually, that is I think gravity balance or whatever we have. 3 Earth radii after giant impact, say. So this is now nicely established theory itself. So since Earth and Moon have formed at the same time, say, so now you can easily translate your the lunar chronology function to Earth itself. So this is how it says actually. So this is the chronology function for Earth. Okay, but on Earth we don't have data like billion years. How many craters was there on Earth? Around 4 billion years, around 3 billion years. We don't have data. But then from the lunar chronological function set, we can easily calculate for our Earth itself. So this is the data. So this is the one. So 3.4 billion years say. So this is the crater density function actual. Okay. Then we have say. So this is 1 billion years, 100 million years. So these are the graphs. And then this whether it works or not, say. Now the easiest way is now already in Earth we have the craters. I showed you, right? These craters are already there. Lunar crater is there, the Chicxulub crater is there in India itself. So people have done analysis and they know the ages of all these craters, and we know when that crater was formed also, because from the carbon dating you can get this information also. So if you plot on this graph, say, you can easily verify whether this method works or not. Okay. So it nicely, this works, it seems. So you can see this is the data, 125 million years, say. So this is the line, the data for our existing craters on Earth, so they agree with this, so this curve has come from the Moon, but then nicely, both of them agree with each other itself, which says, this methodology, say, from Moon, the transfer things, nicely works, and then one can use this for other planets itself. Okay, so this is a very easiest methodology. So just 4 steps only. Okay. So why Moon is very well studied? The reason is Moon is like a fundamental thing for us. Okay, because from Moon you can understand our Earth history, you can understand other planets also. So this methodology also has been derived. So the lunar craters, size, frequency, distributions, Apollo missions, the data. Now you have to do this 4-step process. Lunar impact velocity is very well known. The projectile thing you have to calculate. That integral equation has to be done, which comes anyway from the total probability theorem. Then impact probability, impact velocity, for your target planets. You can easily, scaling laws, you can easily calculate, and the same integral equation has to be done. Now you find out the left hand side. Initially you found out the left hand, this right hand side. Now you calculate this itself actually. So this is a easy methodology which works nicely in practice. And if you see many papers, they have reported this, like Mars, say, they have transferred, for Venus, other planets also by using the Moon. So the geological ages has been done. Okay. So like these type of graphs have been done, like Earth, say. So this is how our Earth crater frequency distribution at 3.4, the billion years itself. Okay. And what happens at 3.4 billion years, say, the assumption is both of them will be same kind of thing. That is how this theory comes into picture. And using this n of 1, you can see here this one. So they find out all this chronological data sets itself. So that is how we draw. So we will know the history of Earth also from Moon itself. So this is how we are trying to understand the geological, what happened on Earth 1 billion years ago, 2 billion years ago. Although we may not have the information, but understanding Moon helps you to understand our planet itself. So this is the most important thing itself. Okay. So anyway, this is the same thing only. So now on Earth they say, right, impacts of craters, say, diameter more than 5 kilometer land occur approximately once per 1 lakh years. So these numbers also people have calculated, like 30 kilometer once per 1 million years, because these are very important, when there will be a large impact on Earth, and all those studies have been done, okay, by this crater, transfer this itself. So Chicxulub crater, say, so this also, it nicely 65 million years somewhere it occurs. Okay. So it also matches with the, which you derive from the Moon also nicely agrees with this data sets itself. Okay. And now coming to the Moon crater, that is a geological age of Moon, say. So for Moon, we have to understand the geological age. Like on Earth, I showed you, right, last time, I think old classes itself, Hadean era, Archean era, Proterozoic, Phanerozoic, Cenozoic, I showed you this one. So for Moon also, based on this crater frequency distribution, they have defined the geological history of Moon itself. Okay. So these are the things. The oldest geological age on Moon they call as a Pre-Nectarian system itself. Okay. So these are the oldest thing. So they say that Pre-Nectarian systems, it comprises all landforms older than the Nectaris basin. So there is one basin is the Nectaris basin. Okay. So the age of this basin is 3.9 billion years. So before Nectaris basin formed, all those things comes under Pre-Nectaris basin itself. So this is like a benchmark Nectaris kind of thing. So all older than the Nectaris basin and includes 30 recognized impact basins. Some directly underlie the deposits of nectaries, and others are recognized as pre-nectarian by the size frequency curves of the superimposed craters. So they are chronologically sequenceable at least. And the oldest recognized basin is Procellar. Okay. Of course, they say it may not be impact origin. The oldest, also the deepest and the largest is a South Pole Atkin Basin, basically. So you can say the South Pole Atkin Basin is the oldest, you can say, in the moon itself. You follow? So so the age is almost around the pre-nectarian system itself. So that's what they say. Now the next is a Nectarian system. So geological, before 3.9 billion years ago. So they call this as a pre-Nectarius. After 3.9 say. So this comes under Nectarian system. Okay. So from the size, frequency, n of 1, everything they have done. So all the landforms say formation of Nectarious impact basin and the formation of Imbrium impact. Okay. So these are two basins. So between Nectarious and Imbrium, whatever happens, it comes under Nectarian system itself. So the most important thing, basins are Serentatious Basin, Imbrium Basin, Crisium Basin, Oriental, Nectaris, all these things, they formed during the Nectarian time itself. So 3.8 billion years ago, 3.89, 3.89, so they all comes under Nectarian system itself. So this is the next geological age itself. Okay. So they, of course, most of the Nectarious thing, they say that, you can find out in, you see, the far side of the moon itself. You will see most of the this itself, the Nectarian things. So it is a near side. So near side of the moon mostly is characterized by Imbrium. That is much more younger than Nectarian. But if you see the far side of the moon, say, so now you will see this Nectarian and pre-Nectarian. The age is extremely old, basically, on the far side of the moon itself. So these are they have found out from the craters only. Okay, the crater side. Now next thing, say, pre-Nectarian is over. Nectarian things are that now comes a lower Imbrian series, basically. Okay, so that's what they say, Imbrian impact basin and the formation of Oriental impact basin itself, whatever has been produced itself. So they say two basins extensively laterally continuous horizons. Of course, Imbrian basin was flooded by lavas. Crater counts, topographic freshness suggests that Schrodinger basin, say, one famous basin is there. I think it is a landing site or something like that. It is a lower Imbrium. And then no basins. So they have easily, and of course, Apollo 16 landed or maybe in this region itself. So this also geologically, they have estimated the ages itself. So now pre-Nectarian, Nectarian, then Imbrium, lower Imbrium series, they say. Then they say upper Imbrium series also. So this extensive Mare, Serenities, Tranquillities, Crisium, Nectaris, Fecundities, Nubium, all this comes under upper Imbrium series. So this has been done based on your crater size frequency distribution and finding n of 1 and then correlating with the data set itself, that is with the Apollo missions itself. So this also has been estimated. Now the next things after the Imbrian things comes the Eratosthean system itself. This is another geological age, basically. Okay. So this they say upper boundary say is a liquid operationally distinction between the subsequent Copernican system was made according to whether a crater was non-rayed or bright rayed. Actually, okay, I have shown you long back that rays also, bright rays, based on that, they have estimated this thing itself. Okay, upper Imbrian places and this one. Yeah. So this includes Oceanus, Procellarium, so all this comes under Eratosthean system itself. The next one, this is how it looks like. Eratosthean basalts, say, and the near side you can see these dark ones are all one age, homogeneous age itself. And then these are all upper Imbrium, basically. They are much older than this itself. So these on the near side and the far side. As already I told you, far side is very older than the near side of the moon itself. Pre-Nectarian, those things will be dominant. Now the next one is a Copernican, the system. So this things started with the rays, basically. Okay, I showed you in the old graphs itself. The Copernicus crater, if you see, a bright rays will be there. Tycho crater, Copernicus crater, say. So bright means it has been formed recently. Okay, recent means not 1 year, 2 year, some million years ago itself. Okay, so they are all superimposed. So this is what they call as a Copernican system itself. So that is how they have defined. Okay, so how many geological ages are there? See, if you see here, one is a pre-Nectarian. Please remember. Then we have Nectarian system. Then we have upper lower Imbrium series and upper Imbrium series. So this is another thing. Or some textbooks they write as Imbrium system itself. Okay, they combine these two also. Then we have Eratosthean system itself. So there is a crater by name is Eratosthean system itself. Then we have the Copernican system. So the most recent thing is the Copernican system. That is what they classified the whole moon into these zones itself. Okay, based on this data sets itself. And then if you plot, the graph also looks like this. You can see Pre-Nectarian, Nectarius, Chrysium. So these are all the basins. And then if you find out N1 of 1, say, and then plot with Apollo data, this itself. So that's the graph I showed you, right? Which is, linear and then exponential kind of thing. So they have fitted this type of graph itself. So this is how the geological ages, has been found out actually. Okay. So the recent one is, Tycho crater, North Ray crater, Cone cell. So these are all the recent, the basins which has been formed on the moon itself. And then if you want to see the geological map, say, so there is a nice, this one. So I will just show you this one itself. Sorry, not this one. So I will just show you where is that. You can see this graph. You can see this image. So the image is visible. Oh, sorry, I think it didn't. You are able to see this one?
Yes, sir. Yes, sir.
So this is a geological map of moon, okay, provided by USGS. It is available online. You can download. You can see they have given like this, okay, Copernican crater, Eratosthenes crater. So these are all the geological ages, okay, Imbrium, Nectarian, this one, and finally, Pre-Nectarian Terra. So this is the oldest one. So like that they have prepared. And now they have given the map, the color indicates, okay. So Pre-Nectarian means, some this type of a color itself, so you can easily identify, okay. So if you want to find out, say, so this, Mare Imbrium, okay, the geological ages. So you can easily zoom up. Now, if you see the Oriental Basin, say, you can see here, Oriental Basin is here. So from this map, from the craters and other things also, they have nicely marked the ages and, all other details from this maps. So this one. So these are geological map of the moon itself. Just based on the craters itself, they have got these numbers itself, okay. So these details also, will be are available, okay, based on this itself, okay. So you can see, so this also they have plotted in the South Pole region, how this graph looks like, and this is in the North Pole, so how the graph looks like, all these regions itself, okay. So this is a geological map of moon itself, okay. So I suggest I will send you the link also. You can easily, type, like if you type in Google geological map of moon, so you will get this details itself, okay. So anyway, so with this, we will, so almost, I think the crater counting things, is, so almost it is fine. Okay. Just one. Now, now. So now with this, of course, I will, close this today's this one. Okay.